To derive Mayer's relation, we need to talk about piston cylinder arrangement, in which we are going to discuss the two positions. One is a fixed position and second one moving piston. The piston can move up and down. In both cases, heat energy is supplied to the piston cylinder arrangement. Suppose an ideal gas is enclosed in the cylinder and heat energy supplied to it. Due to the heat energy, temperature of the gas changes. And due to change in the temperature of the gas, a considerable change in the volume as well as considerable change in pressure of the gas is observed. Therefore, for gases, we need to talk about two types of specific heats. One is the specific heat of gas at constant volume and specific heat of a gas at constant pressure. Specific heat at constant volume is denoted by Cv, and specific heat of a gas at constant pressure denoted by Cp. For gases, specific heat depends upon physical conditions under which we add heat to it. In all scientific calculations, whenever we talk about specific heat for gases, it is expressed in terms of molar specific heat. So, molar specific heat is given by formula Q divided by N. Q divided by N is nothing but the heat per mole. Heat per mole. Because N equals to total number of moles of the gas and Q equals to total heat energy supplied to the gas. That is, let us understand, suppose this is a cylinder. In this cylinder, there is a gas. So, we don't know how much is the gas. So, it is a quite large amount of the gas. It is not 1 mole. So, whenever you are heating the gas, it is, suppose the total heat supplied equals to Q. And in this given quantity of gas, there are the N moles of the gas. So, we need to find heat supplied per mole. So, total heat divided by total number of moles. This will give heat supplied per mole. Okay? And when we are heating the gas, temperature of the gas changes. So, suppose T1 is the starting temperature and T2 is the final temperature. So, when we are heating the gas, the temperature of the gas is changing. So, change in the temperature is T2 minus T1. Let us call it delta T. So, delta T nothing but change in the temperature of the gas which is being heated up. So, now the molar heat capacity is nothing but the heat supplied per mole divided by delta T. Delta T nothing but change in the temperature, and this temperature can be calculated in terms of Kelvin or it can also be calculated in terms of degree Celsius. So, in all scientific calculation, the specific heat of a gas is expressed in terms of molar specific heat. Let us define it. So, definition is, it is the amount of heat needed to raise the temperature of 1 mole of gas by 1 degree Kelvin, or it can also be expressed in terms of 1 degree Celsius. Therefore, molar heat capacity equals to Q divided by N divided by delta T, where Q equals to heat energy added to the gas in joules, N equals to total number of moles of a gas, and delta T equals to change in temperature in Kelvin, or it can also be calculated in degree Celsius. Mostly we deal with Kelvin. So we have two types of specific heats for gases, that is Cp and Cv. Mayer's relation connects these both specific heats by relation Cp minus Cv equals to R. This relation is called as Mayer's relation. In general, heat absorbed equals to product of mass and specific heat and temperature change. Here we are considering gases So instead of mass, we shall be taking here moles. And heat absorbed at constant volume process, let us call dQ1, and heat absorbed by the gas at constant pressure process, let us call dQ2. For constant volume process, dQ1 is equals to change in internal energy. This is equals to number of moles multiplied by specific heat and temperature change. Since we are taking the small change, therefore in place of delta T we can write dt, and number of moles n equals to 1, therefore dq equals to 1 multiplied by Cv multiplied by dt, therefore dq1 nothing but heat absorbed by the gas at constant volume process, dq1 equals to Cv multiplied by dt, call it equation number 1. And in case of constant pressure process, dq2, that is heat absorbed by the gas, is again multiplication, the product of n, Cp and dt. In constant pressure process, we multiplied by Cv, and in constant pressure process, we consider Cp. But number of moles are equals to 1, therefore dq2 equals to Cp dt, call it equation number 2. One more important thing, in case of constant pressure process, dq2 is also equals to change in internal energy and plus work done, call it equation number 3. Now managing all the three equations, putting the values of equation 1 and 2 in equation 3. So putting 1 and 2 in 3. So dq2 is nothing but Cp dt equals to dE nothing but Cv multiplied by dt plus work done, bringing Cv dt this part to the left side. So minus Cv dt equals to dW. dW is nothing but work done. It is calculated by product of pressure and change in volume. Therefore Cp dt minus Cv dt is equals to P into dV. But P into dV is nothing but it is equals to R into dt from gaseous equations. Therefore Cp dt minus Cv dt equals to R into dt. Now taking dt common, equals to R into dt, cancelling dt both sides, we get Cp minus Cv equals to R. So Cp minus Cv equals to R. This equation, this relation between Cp and Cv is known as Mayer's relation.